Hello, today we're gonna talk about algebraic geometry codes and code equivalence. As usual, we have a non-singular curve over FQ, which we call V because we might use the letter C to denote codes, so not to confuse it. And we have a divisor D on the curve. And now let's define what we mean by equivalence. So two codes C prime are called monomially equivalent and will always two linear codes and will always mean monomial equivalence if we talk about code equivalence. And now there are several ways we could define it. We define it by if there is a linear isomorphism between C and C prime that is also an isometry. And isometry with isometry I mean with respect to the Hamming distance. And you could also define it by looking at a generator matrix and then multiplying it with a monomial matrix. That's why it's called monomial equivalence. Or a linear isomorphism that respects the distance. We'll use that later. So it's enough that the distance of code words is preserved under this linear isomorphism. Okay, and it's quite easy. It's actually obvious that at least the code parameters stay unchanged under monomial equivalence. So the dimension stays the same because we have a linear isomorphism. Oops. And the minimum distance stays the same because we have an isometry. So let's see now what happens if we replace our divisor D. So now we see what happens if we replace the divisor D by some D plus the divisor of some function. So let's call it D plus G. So the class of a divisor is just the set of all these D plus G. So if we get that we so what we're going to show is that if we replace D by D plus the divisor of G, we get a monomially equivalent code, which means that the code's parameter remain unchanged, and so we don't really care about which divisor from the class we take. And of course, G is in the function field of the curve. Okay, so let's look at this now. So let's say we have an F in this. So we always looked at these spaces, L of D plus G. And what was this? Well, this was equivalent to F plus G plus D being non-negative, which in turn is equivalent. So F, the divisor of F times G, is just the divisor of F plus the divisor of G. So this is just by properties of the discrete valuation. And so we have this, and well, this tells us just that f times g is an L of t. Okay, and what we get from here now is that if we so this is the multiplication map with g, so we view this as a map from L of d plus g to L of d, so g is invertible, so we can also take the backwards direction, so this is an isomorphism, which tells us soon that at least so let's look at now. So we know that the degree of a principal divisor, so of this divisor of G, is 0, so this is the degree of D. And this tells us now that the codes have the same dimensions. So if we have the dimension of a code was just the dimension of this space, respectively this space, and well, these spaces are isomorphic, so the codes we construct from these two divisors have the same dimension. Okay, now let's fix some notation, and then let's show that that we get monomially equivalent codes. So let's denote by points. So this means just the points at which we evaluate the points. So these are P1 to Pn. So we evaluated these points. And we write for simplicity the principal divisor G. So this is the sum. So this is just a sum nu p of G times P, and we can write this as sum over nu pi of G times pi plus a sum over the p which are not in these points, nu pi of G, nu p of G times P. Okay, and for simplicity, we also call these nu pi of G pi. Okay, and now let's see. So we have L of D plus G. We have an isomorphism to L of D. We have a map to the code, which we get by the divisor D plus G if we evaluate functions at P1 to Pn. And we have a code if we evaluate with the L of D space at P1 to Pn. Okay, and also these maps are isomorphisms as we've seen last time. So we can just go backwards, so we go in this direction, and we get an isomorphism here. So we have linear isomorphism, so that's clear. What we have to show is that this is an isometry. So in order to do this, let's have a closer look at the map. So D plus G. So again, we split this D in some D prime, which has support disjoint from the points, plus the sum bi pi. So this is D. And so then we have plus the divisor of G, which is the sum over the capital P, which are not in the points, nu P of G times P. Okay, and now we can reorder this a bit, so this is just D prime plus the sum of the one which are not in the points, nu P of G times P, and then plus sum over the BI plus PI. Okay, and of course this thing here has also support disjoint from the PI here. Okay, and now let's see. So on the left hand side, the evaluation maps to evaluation. Or let's pick a thing in here, and that's of the form some evaluation of something, and the evaluation was just T1, and then we have to look here. So we have B1 plus P1, F of P1 up to Tn to the Bn plus Pn, F of Pn. Okay, and now if we go this isomorphism in the reverse direction, this maps us. So let me maybe make it in colors. So this gives us F. Then we get 2 F times G. And then we have this blue map here. And this blue map gives us, so let's see what this gives us. So this gives us, so now we have the divisor D. So we just have the BIs. So we have T1, B1, but now we have F times G. So we have FG of P1, and so on up to Tn to the Bn, Fg of Pn. Okay, and now let's check that this is an isometry. And as I mentioned before, it's enough to check the weight. So let's just check the weight. And what we're gonna show is that we get a 0 here, if and only if we get a 0 here. So we get a 0 at position I, if and only if we get a 0 at position I at the other element in the code. So let's see. We have Ti to the Bi plus Pi F of Pi. This is 0 if and only if our discrete valuation of this thing is bigger than 0. This is equivalent to, so Ti is usual. Let me make Ti a little bit clearer. So Ti as usual has valuation 1. So we get Bi plus Pi plus the valuation of F bigger than 0. But now let's remember the notation. So this notation was just that. What's this? Yeah, here we had it. So this is this notation. So this is just nu Pi of G. And now again we use properties of the discrete valuation. So we get just that bi plus new pi of f times g is bigger than 0, but this is if and only if ti to the bi f times g of pi is 0. So we have this is 0 if and only if this is 0. And that's what we wanted to show. And this finally gives us that if we have two equivalent divisors, which we write by this, then we get C so this was the proof, and just to make it clear, so then these codes are equivalent. So and C of E of P1 to Pn are equivalent. Okay, that's it for this video. I think probably at some point there'll be some more videos about algebraic geometry codes, but let's see when and what about, but I'm not sure yet. So thanks for watching, have a good day, and bye.